Welcome back to the fourth quarter of complex numbers. In this quarter, we are going to talk about complex functions. Here we shall try and understand complex functions, its plotting, we shall deal with some examples and iteration. In fact, we are going to recall the definition of a function, then we shall raise complex functions, we shall graph complex functions, we shall deal with some examples, we shall deal with some complicated functions, then iteration of functions, and finally GSA. A mathematical function f is mapping of a set A to B is a rule that assigns to each element of A exactly one element of B. Let us deal with a simple example. Function f is mapping from real numbers to real numbers, real set of numbers, and y equal to f of x we say, and f of x is equal to x square plus 1. So if you want to try a graph for y equal to f of x, where f of x is x square plus 1, you have to simply arbitrarily, independently select values of x and then estimate values of y and make a smooth plot of those points. Let us suppose that x is equal to 0. When we substitute x equal to 0, we have function which is y that is equal to 0 square plus 1. So that brings us to this point 1. Then we are having x equal to 1. 1 square plus 1 will be 2. It will be somewhere here. So 1 square of 1 plus 1 will be 2. Then 2 square plus 1 will be 4 plus 1, 5, and so on. Now let's deal with a complex function. The complex function f is having a mapping of set of a complex number onto another set of complex number. Let us suppose that this function in general is represented by f of z, where z is a complex number. Basically, you have to mind z is equal to x plus I y, and then the function is z square plus 1. Now the immediate question that pops in our mind, how do we graph this? Do we need 4 dimensions to have a plot? As I said, just we shall start writing z is equal to x plus I y. Now the function f of z we assign to be w. So z is a complex number, w is also a complex number. W is equal to f of z, and f of z we have z square plus 1. So we have to work out x plus iy whole square plus 1. So expand this bracket as a plus b whole square. Simplify, use I square equal to minus 1. You will end up with x square minus y square plus 1. This will be the real part of the answer. And 2 times xy times I, this 2xy will be the imaginary part which is associated with I. Now we have 2 real functions. X square minus y square plus 1 is a real function, and twice xy is also a real function. Let us attach a real function u as function of x and y, which has functional variation given by x square minus y square plus 1. Let us imagine another function v that is depending on 2 variables x and y, and the function is 2 times x, y. Thus, here we have 2 functions u and v, and we are having mapping from r square to r. Now we shall attempt graphing of complex functions. The idea is that we have two complex planes. The first plane we shall reserve for domain of the function, and second one we shall reserve for the range of the function. Now we have z plane wherein we are considering the complex number and we are operating function on the complex number, and what we are going to get is a w plane wherein we have basic dependence w is equal to f of z. So here we are going to look at two planes to clear our concept. In technical terms, we are going to analyze how geometric configuration of z-plane are mapped under the function f to the w plane. So let us try a hands-on experience on the same function, similar function. Let us suppose that f of z is equal to z square and w will be obviously x plus iy whole square. So you have to expand the bracket a plus b whole square as a square plus b square plus twice ab. So herein we are going to do the same thing and you will end up with what you are having on right side on your screen. But if you look at these equations, these are not very useful for plotting purpose. We shall refer the same equation in polar coordinates. Probably you will find that it is more advantageous. Instead, z is equal to x plus iy. We will have transformation of that equation into polar form, and we prefer to write z is equal to r times e to the power I theta, and then w is equal to square of z, so it will be simply r square into e to the power 2 times I theta. So that here mod of w, mod of this complex number will be mod of z square, that is it is square of the modulus of the basic complex number, and argument of z is twice the argument of z. Argument of w is twice the argument of z. So thus we have same equations on the beginning of this slide. So what is happening here, as z moves around a circle of radius r once, w moves around the circle of radius r square at double speed, that is twice. So that here z is represented by a circle of radius r and we have theta rolling over 2 pi, so that it describes the circle once. When we have w equal to f of z, we have a circle of radius r square instead of r, and here this is revolving twice. So the story is that we are having one revolution and then one more revolution. This is the result of the functional operation f on z that makes a complex number w, and here we are in the w plane. Now that your argument is having some angular variation a little above 90 degree, and that is in z plane. So in w plane it will be more than 180. So this diagram precisely represents z plane here and w plane over here. Now that we shall march over to a little complicated function, let's go one step ahead and let us differ with the earlier function by a simple step plus 1. So f of z is equal to z square plus 1. Now here we shall move in a step. We shall move from z to w1, where we have function w1 equal to z square. This already we have done. And then we shall move from w1 to w, so that we make the complete stride of representing z square plus 1. So this already we have done. W1 equal to z square, this we have already done. Whatever radius you are considering, that radius square is involved here. So in W1 plane we have radius square of z, that is here radius is mod z, and in this case the radius is mod z square. This we have done, whereas the argument is double the angle. So whatever angle here we are considering, so that is doubled in this case. Now next step we are adding plus 1. So the moment we add plus 1 is a real number which is added to the complex number w1. This makes displacement of this circle of radius z square to a new location wherein the center is 1 on real axis and 0 on imaginary axis. And again, the radius of this is z square. Now we shall go one more step up. F of z is equal to z square plus c. Instead of 1 we are having here c, and this small c is belonging to the set of complex numbers, where set of complex number we are representing by capital C double bar. Now the center has to be located to a new location which is represented by the complex number small c. So here we can go stepwise from z to w1, where the radius is in first case it is mod z, and in the second case it is mod z square, and then we are adding a complex number so that the center is displaced from origin to a new location, and that new location is defined by the complex number c. Now friends, we are in position to understand the iteration of function. Let us suppose that f of z is equal to z plus 1, a simple function. Then we define f square z. That is, this is not simple square that we are considering. I should say f2 z. That is f of z. This is called iteration. So f of z is basically z plus 1. So I want to replace this f of z by z plus 1. Then we have to again find out the function f of z plus 1. So the variable now is z plus 1, and plus 1 when added to that, it makes that complete function. So in all it will be z plus 2. Now f cube z will be f of f square z. We have already estimated f square z, and then we shall substitute f square z is equal to z plus 2, and then f of z plus 2 will be z plus 2 plus 1, that will give you z plus 3. So you can generalize the iteration operation, and fnz will be z plus n when f of z we have z plus 1. So here very clearly I wish to mention that f to the n is here nth iterate of f. It is not to be confused with the nth power of f. To understand it further better, let us consider that f of z is equal to 3z, and then we are having iteration of f of z, that is f to the 2 of z. So f of z is 3z, so we are replacing the variable f of z by 3z, so that we can find f of 3z. It will be 3 times 3z, that is 3 square z. So the third iteration of z will be f of second iteration of z, and second iteration of z we have got 3 square z. So 3 into 3 square z will be 3 to the power 3z. So here we can generate the nth iteration of f of z as 3 to the power n z. Now a new function f of z is equal to z to the power d. Then second iteration of f of z will be z to the power d to the power d. So that is z to the power d square. So we can generalize for nth iteration of z. F of nz is equal to z to the power d to the power n. Now one more example, let us suppose that f of z is equal to z square plus 2. Then second iteration of the same function will be f2z equal to z square plus 2 to the power 2 plus 2. So this will be z to the power 4 plus 4z square plus 6. Now in the similar fashion we can go on finding the higher iterations and generalize here that nth iteration of the function is a polynomial of degree 2 to the power n. To study the Julia set of polynomial f of z equal to z square plus c, we'll study the behavior of the iterates of f square, f to the 2, f to the 3, f to the 4, f to the n, and so on of this function. The Julia set of f is the set of points z in the complex plane at which this sequence of iterates behaves chaotically. We thus need one more preparation. We need to study sequence of complex numbers, which is our next topic.